Hello everyone. So, welcome to my talk, All Your Secrets Belong to Us, Leveraging Firmware Bugs to Break TEs. A little bit about me. My name is Dohrmann. I love doing low-level stuff, so if I have a chance to talk directly to the hardware, that's what I want to do. I really enjoy writing code, but I also enjoy breaking code. And today we'll mostly be doing the latter. Okay, so what will we be talking about today? First off, we'll give a little bit of an introduction about what a TE is anyway. Then we'll talk about one specific implementation, the one by AMD, which is called AMD SEV-SNP. Then we'll talk about some of the implementation details that we need to understand the bugs. Then we'll actually talk about our first bug. Then we'll talk about the maybe most obvious but not necessarily best way to exploit such a bug. Then we'll come up with an even better way to exploit this bug. Then we'll talk about the second bug. Then we'll also talk about how to exploit that one. And in the end, we'll have some wrap-up and takeaways. So, what is a TE anyway? TE stands for Trusted Execution Environment. The basic idea is to have a secure part of the main processor where applications can run securely even if other parts of the software stack have been compromised. Notably, this also includes the kernel or the hypervisor, so even if either of those have been compromised, the application should still run securely. And so this threat model is also very different compared to a lot of other applications. For TEs, the main threat really is leakage of secrets. So if you have an info leak, this is pretty much as bad as it gets. The reason for that is that once you have the secrets, you can impersonate the TE, and you can just run the application outside of the TE where it's not protected. And so, of course, if you can achieve arbitrary code execution, that's one way of getting the secrets out. But really, the main part that you want to protect is the secrets. There are a lot of different implementations by a lot of different hardware vendors. Some of them are a bit older, but some of them are also quite new. And that's why there's also another talk. So today we'll just talk about AMD SEV, but later this afternoon there's also another talk about Intel TDX. So maybe if you enjoy this talk, you might also want to check out that other talk. Okay, but as I said, for today we'll just focus on AMD SEV-SNP. So obviously this technology implements a TE, and SEV stands for Secure Encrypted Virtualization. From this, you can already gather that the whole point of this is to protect entire virtual machines from a potentially malicious hypervisor. And so the way this works with conventional VMs is that the hypervisor has access to all of the memory that's owned by the VM. However, AMD SEV-SNP actually implements a hardware extension directly in the CPU that makes sure that all of the memory that's owned by the VM is first of all encrypted, so that the hypervisor can't just read the secrets, but all of the memory is also integrity protected, and yeah, that way the hypervisor can't tamper with the guest like it could potentially do with a regular VM. What's also interesting is that when the VM is first booted up, all of the memory contents are actually measured, and then later those can be attested through attestation reports. So if you're familiar with TPMs, the basic idea is the same. While the platform is, or the operating system is booted up, you load in all of the additional code, and in the end you can remotely attest that. Okay, so let's actually talk a little bit about how this is actually implemented. And the first thing we have to talk about is the platform security processor. So the platform security processor actually exists on all AMD CPUs. It exists outside of the context for SEV, and it's responsible for a lot of stuff during early boot stuff. So for example, before the x86 cores even start running, the PSP is already running and doing a lot of setup in order to get the machine to boot. So if you're familiar with Intel's management engine, this is sort of the same thing, but for AMD. However, in order to do all of those things, the PSP needs to be very privileged, and this is also why it's very natural for the PSP to also play an important role in SEV. So basically, the way you can think of it is that the CPU itself can run the virtual machines, but for everything but running the virtual machines, you need the PSP. So notably, this includes a lot of management stuff. So if you want to create the VM, if you want to delete the VM, but also if you want to attest the VM, you need the PSP to do that. And so the PSP also holds a lot of the cryptographic material that's actually used to securely attest the VM. Today we'll just be talking about SEV-SNP, but there have actually been two other predecessor technologies, and those actually use the same firmware, because even though there are a lot of big differences, they also share a lot, and that's why the same firmware is used. What's really interesting, though, is that at the end of last August, AMD actually published large parts of this firmware, and this is this was the first time that a lot of researchers like me could actually take a look at the firmware and verify those claims made by AMD. Okay, so next up, we'll talk about the reverse map table. So I already told you that all of the memory is integrity protected, and it's also encrypted. For now, we'll just talk about the integrity protection part, and we'll talk about the encryption later, but yeah. So the reverse map table is a really large table that is used to track the ownership state of every 4 kilobyte chunk of memory on the system. The basic idea is that most memory starts out as being owned by the hypervisor, but as the hypervisor wants to launch different VMs, it can actually assign memory to those VMs by changing the RMP to reflect that. And then for every single write to memory, the CPU internally checks the RMP to make sure that the entity that is currently running is actually an entity that owns that memory. And so this all is done to make sure that no memory is written to by the hypervisor to a guest that doesn't, Also, a guest can't write to another guest's memory, so that this is also tracked in the RMP. Interestingly, for the CPU, this happens automatically for all access levels. However, for the firmware, this is not always the case. The reason for that is that, as I already mentioned at the beginning, the PSP is very privileged, and so in principle, it can write to any memory it wants. However, in practice, the PSP actually does a lot of access checks to make sure that the PSP also only writes to memory that it owns. So memory can not only be owned by the hypervisor or by the firmware, some memory is also actually owned by the firmware, and so the firmware also does those checks. At this point, you might be asking, how is this RMP actually managed? There are two ways to do that. The first one is for the most simple and obvious cases. This is actually done using special CPU instructions. So for example, if the hypervisor wants to assign some memory to a guest, this is fairly straightforward, and so there's a very simple CPU instruction to do that. However, for more complicated stuff, like if you want to do memory swapping or if you want to move memory around, you actually need the SEV firmware for that so that it can handle some of those more complex cases. And so in the end, a lot of sensitive information that shouldn't be tampered with is actually stored in just regular memory that is protected by the RMP. And so this whole system also places a lot of trust into the RMP checks being enforced correctly. And this is also where things will go wrong today. And we'll see where that leads to. OK, just another quick visualization. On the right hand, you can see a lot of different memory chunks. And on the left hand, you can see the RMP. So the RMP tracks the ownership state for every chunk of memory. In practice, those chunks are usually a lot smaller, but it doesn't really matter. So you can see most memory is owned by the hypervisor. Some of this is owned by different guests, and some of it is actually owned by the firmware. Interestingly, though, because the RMP is just stored in regular memory, the RMP itself also has an RMP entry. And this is actually a really good example for memory that's owned by the firmware. The reason that it's owned by the firmware is that we don't want the hypervisor or the guest to directly write to the RMP. We only want to allow accesses using those special CPU instructions, and we want to forbid all other write accesses. OK. And so with that, we actually have all the necessary prerequisites to talk about our first bug. And OK, so let's do that. So this first bug is related to command dispatch. As you might remember, the hypervisor asks the firmware to do a lot of stuff on its behalf that it can't do using CPU instructions, and it obviously needs some way to tell the firmware what to do. And so we'll briefly walk through how that works. So the first step is that the hypervisor actually writes the request somewhere to memory that is owned by itself. Immediately after writing that request, the hypervisor then donates that page to the firmware. It does that using one of those special CPU instructions that can be used to change the RMP. The hypervisor then tells the firmware about that request. The firmware reads the request, executes it, and writes it back. At this point, the firmware tells the hypervisor that it's done processing. The hypervisor reads back the response. And the last step is that the hypervisor asks the firmware to reclaim that page so that we don't just leak out a page to the firmware state for every request. And so the long story short is that just commands and requests are just written to regular memory. However, there's one thing that's sort of important, which is that during step 6, the firmware really needs to make sure that the memory is actually owned by itself. Because once again, every entity is only allowed to write to memory that is owned by itself. Okay, so this is all very nice. However, it turns out there are actually a lot of commands that just don't have a response. The firmware has nothing important to report back, and so this allows us to skip a few steps. So the first step is just like regular. The hypervisor still writes the request to that memory location. However, then it doesn't need to donate the page to the firmware state. We'll see in a second why it doesn't need to do that. Most of the stuff continues like normal until the firmware processes the request. But then, importantly, the firmware doesn't write back a response. That's sort of the whole point. For some commands, you just don't have a response, and so you don't need to write back a response. And that's also why the page never had to be donated to the firmware in the first place. The firmware never does a write to it, and so the firmware doesn't need to own that memory. Okay, and so most of the other stuff is like normal. The hypervisor obviously doesn't need to read the response back, and it also doesn't need to reclaim the page. And so in the end, this is a really nice optimization that allows us to skip 4 of the 9 steps and, yeah, gain some nice performance improvements. And so the conclusion from this is that, well, it's a bit complicated. In some cases, the firmware actually needs to check that it owns that memory, and in some cases it doesn't. It really depends on the command. And the way this is actually implemented is that the firmware has a big table for every command. It lists the buffer type and whether or not RMP write checks need to be done. So for example, for the init command, which is used to initialize the platform, this command only reads an input. It doesn't write back an output. And so no RMP checks need to be done because the firmware never does any writes. But for example, the platform status command only writes back an output. It obviously writes back the status of the platform. And so because the firmware is now doing writes, it needs to check the RMP to make sure that the firmware is actually allowed to do that. And so this is all very nice and well and works quite good for most of the commands. However, if you look at this table, there is one exception to this rule, which is that for some reason, the attestation command doesn't do RMP write checks. The table just says false there. However, the attestation command still writes back an output. I'm not quite sure why this is. My guess is either it's a typo or a copy-paste mistake, but either way, let's look at what we can do with that. So instead of using normal memory that's owned by the hypervisor, the hypervisor can actually point the firmware to memory that's owned by a guest. And remember, all memory that's owned by a guest is supposed to be encrypted, integrity protected. So obviously, the hypervisor can't write requests to that location because it can't do writes. It also can't donate the page to the firmware. But none of those cases, none of those things really matter here. And the important thing is that the hypervisor can still tell the firmware that there is a request there that it should execute. And the firmware will do just that. And importantly, it will write back a response to that memory that's owned by the guest. And this is really the bad thing here, because the hypervisor was just able to trick the firmware into writing to memory that it wasn't supposed to write to. The hypervisor doesn't have write access to that page, and the firmware shouldn't have write access to that page also. And so this is really bad. Okay, but yeah. So once again, the hypervisor can send a malicious attestation command to the firmware and then write some memory back to the guest memory. A little bit about this memory corruption. So the attestation command is, as the name might suggest, used to generate attestation reports. And so the actual body of the attestation report is written somewhere completely else. And the only thing that's written back in the request and response buffer is actually the size of the attestation report, because that's the only thing that's of fixed size. And so in practice, the attestation report will always have a fixed value. And so the value that's actually written back into guest memory is also always fixed. It's also always hex D0. And so, yeah. However, what is quite nice is that we can actually choose the location. So we can just shift the request and response buffer over a couple of bytes. And so we have some leeway in that regard. But unfortunately, the value is fixed. OK, but if you remember all the way to the beginning, I told you that the main threat for TEs is leakage of secrets. And so far, we've done like the opposite. We can potentially destroy secrets, but so far we have no way to really get at the secrets, and that's, of course, what we want to do. OK, so there are a couple of problems with attacking a guest directly. So if you want to attack guest memory, the first most obvious thing that we need to know is that, well, what kind of memory do we want to attack? And this is made really difficult by the fact that, well, all guest memory is encrypted, and so we have no way of actually knowing what the memory is being used for by the guest. There are probably some ways to guess that based on the access patterns, but it's by no means trivial, and will probably also have to depend on the specific guest that's running. So, yeah. Next up, and this is perhaps the even bigger problem, is that, well, I told you that all guest memory is encrypted, and this memory corruption that we have here only allows us to write to the ciphertext of that encrypted memory. And so the big problem is that this is using AES encryption, and we have no way of knowing what the corresponding plain text will be for that corrupted memory. And this, once again, makes targeted attacks really difficult and definitely not easy to pull off. And so this all leads me to conclude that attacking a guest directly by attacking its memory is probably possible. However, it's not easy. And exploits will also likely have to be tailored to specific workloads. So if you want to attack Windows, you have to use different strategies compared to when you want to attack Linux, and so on and so forth. And this led me to another idea. What if attacking the guest directly, we attack memory that's actually owned by the SEV firmware? So we already talked about how the RMP is owned by the firmware, but the firmware actually uses some other memory as well, and we'll talk about some of that now. So one of the really important things that's owned by the firmware is the so-called guest context page. So for every single virtual machine that's launched up by the firmware also separately maintains a so-called guest context page. This guest context page mainly contains metadata about the guest. So for example, is the guest currently running? What are some of the field flags? What are some of the encryption keys and so on? And yeah, so obviously guest context pages are encrypted, owned by the SEV firmware. That's why we're talking about them. And they're also denoted using a special state in the RMP to make sure that the firmware doesn't confuse it with other memory that is owned by itself. Also, what's really interesting is that guest context pages are encrypted, and they're actually encrypted using a special key that is only accessible to the firmware. So neither the guest nor neither the hypervisor nor any of the guests have access to the special key, and really there's no need for them to access this page, so it makes sense to use a separate key just for guest context pages. Okay, and so let's actually take a look at some of the fields contained in such a guest context page. As I already told you, there's a lot of crypto stuff in there, some states and some flags. But for now, we'll just focus on one of the fields, which happens to be the very first field, and that is the UMC context seed. So UMC stands for Unified Memory Controller, and basically when the firmware launches the guest, it randomly populates this UMC key seed with random values. Later, during the boot stages, the firmware then actually uses this key seed to tell the memory controllers, the unified memory controllers, about this key, and then the memory controllers will use this key seed to deterministically derive the encryption key that's used by the guest. Yeah. So it turns out that a lot of CPUs actually have multiple memory controllers, and so the firmware needs to tell all of them about this UMC key seed so that they share the same encryption key, and that's also why they need to deterministically derive the actual key from this key seed. What's really interesting, though, is that if we use this memory vulnerability I talked about, and we point a request and response buffer in such a way that it points just at the beginning of the UMC key seed, we can actually corrupt the UMC key seed. And so if we just do this once, we can corrupt the first 4 bytes. But however, we can, as I told you, adjust the location of the memory corruption. And so if we do the same thing 1 byte over, we can actually corrupt another byte. And if we do that a couple of more times, we can actually set the whole UMC key seed to a fixed value. And this is interesting for the following reason. If we have 2 identical guests with 2 identical UMC key seeds, the encryption keys used by both of those guests are also the same. Usually, every guest is launched with a unique encryption key for obvious reasons, but if we use this vulnerability and target the UMC key seed field in the guest context page, we can force multiple guests to use the same encryption keys. And so the idea then is to have a normal victim guest that we can use for all the attestation stuff, And for this guest, we don't enable debugging. However, then we also have a second guest, and for this guest, we actually enable debugging. And the idea then is because both of the guests use the same encryption keys, we can use this attacker guest to decrypt the memory that is owned by the victim guest. And that way, we can leak secrets. OK, so this all sounds very nice. However, there are actually some problems with that, some challenges. And the first one is that, well, I just told you, guest context pages are encrypted. And so once again, we can only write to the ciphertext. And if we write to the UMC key seed, we can only write to the ciphertext, and we have no way of knowing what the plaintext will be. This is made even worse by the fact that, well, encryption is actually dependent on the location of the memory. So this is very similar to like disk encryption. You don't want the same data encrypted at two different locations to have the same ciphertext. So you have an initialization vector that's dependent on the location. And so depending on the location, the ciphertext and plaintext pairs will be different. And this sort of throws off our whole exploit, because the whole point was to have the plaintext of the UMC key seed to be the same. However, if we do this at different locations, this won't work. And so the takeaway from this is that, well, if we want to do this, we have to use the same location for both guest context pages. However, obviously, there's no way to have two things at the same location. And so what we really have to do is that we first have to shut down the victim guest. And only after it's been shut down can we create a second guest context page at that same location so that the location-dependent encryption is the same, and so that we get the same fixed plaintext out. OK, and with that, we actually have all of the steps that we need. So the first step is that we launch the guest like normal. But immediately after doing that, we issue malicious attestation commands and point them at the UMC key seed in that guest context page. We then run the guest, and while it's running, we record some of the memory that we potentially want to decrypt later. Eventually, the guest is being shut down. At this point, we can launch a second attacker guest at the same location. During the launch process for this guest, we actually enable debugging. Then once again, we use the same malicious attestation commands to corrupt the UMC key seed with the same fixed values. Because the values are now the same for both of the guests, they share the same encryption keys. And so if we issue debug commands to that attacker guest, we can actually successfully decrypt the memory that was owned by the victim guest. And so I've actually written some proof of concept code for this. It's partially implemented using some hypervisor patches, but there's also a user space component for this. And for this proof of concept, I've just told the user space component to decrypt some memory at a location that was previously used to store a so-called secrets page. So this is not really that important, but basically when the firmware launches each guest, it creates a special secrets page that's entirely secret just to that guest. And the reason that I've chosen to attack this page is that, first of all, it's very important in the context of SEV. And second of all, it's also very recognizable. So for example, you can see the first byte is always a 3. There are also a lot of zeros, and this really seems to confirm that we were able to successfully exploit all of this. Also, if we parse out some of the fields, they make a lot of sense. So for example, in the third row, you can see the FMS field, which stands for family, model, and stepping. And this matches the value that you would expect for an EPIC Milan CPU, which is the CPU I used to test this with. And so really, this works very well. OK, so with that done, let's actually talk about a second exploit, about a second bug and a second exploit. So this bug is not related to command dispatch at all. It talks about something completely else. This bug is all related to certificate storage. So the firmware stores some certificates, and it wants those certificates to survive across reboots. And so usually, it would store those certificates on an SPI flash. However, for a lot of reasons, you don't really want to use an SPI flash on ELS. You have to. They are like sort of slow and have limited write cycles. And so eventually, AMD added an extended version of the init command that could be used by the hypervisor to tell the firmware to use regular memory instead of the SPI flash. After this has been done, it's then the responsibility of the hypervisor to save and restore this memory. And by doing this, we can skip the SPI flash completely. Of course, because this memory will then be owned by the firmware, the RMP also needs to reflect that. And so once again, before this command is actually executed, the hypervisor issues those special CPU instructions. to make sure that the memory is owned by the firmware so that the firmware can actually write to it. And so as you might expect, during the initialization command, the firmware also does those checks and enforces them, and if the state isn't correct, it fails. What's interesting, though, is that those checks are only done once, and so for all subsequent accesses, the firmware doesn't check the permissions anymore. And this, once again, this is just done for performance reason. The firmware knows that it owns that memory, and so there's really no reason for it to do those checks again. OK. On a completely unrelated note, there's actually a command that the hypervisor can issue to reclaim memory. So the prime use case for this is that, for example, after a VM has been shut down, the guest context page that used to be associated with that guest is no longer being used. And so in theory, it could be used by the hypervisor again. But because it's still owned by the firmware, it can't just do that. However, if the hypervisor asks nicely, the firmware will just give that memory back to the hypervisor. Of course, the firmware doesn't just blindly trust the hypervisor. So it actually does a lot of permission checks to make sure that, for example, if it's a ghost context page, that the guest really isn't running anymore. And so all of this is supposed to be secure. However, there's one big caveat, which you might have guessed at this point, which is that, well, the page reclaim command forgot to check whether or not the memory is being used to store certificates. And this is really bad because the firmware still thinks that it owns that memory. However, it just gave back access to that memory to the hypervisor to do whatever it wants with that. And so this allows us to do the following. The first two steps are just like normal. The hypervisor donates some memory to the firmware and then uses it to tell the firmware to use it to store certificates. However, immediately after doing that, it does something bad, which is that it can use the page reclaim command to reclaim that memory from the firmware to the hypervisor. This isn't supposed to happen because the firmware is actually still using that memory, but because that check doesn't exist, the firmware just allows this. Once the hypervisor actually owns that memory, it can do whatever it wants with that. And one of the things that it can do is that it can assign the memory to a guest. And then the worst part of all of this is that the hypervisor can actually issue some commands to the firmware to refresh some certificates. And by doing that, the firmware will write to that storage location. And of course, because that memory is now owned by a guest, the hypervisor will write to memory that's owned by a guest. Once again, this is really bad. The firmware really isn't supposed to write to memory that's not owned by itself, and it isn't supposed to write to memory that is owned by a guest. And also, the hypervisor isn't supposed to be able to trick the firmware into doing so. OK, so the interesting question is, though, can we do better than last time? So last time, we were really limited by two things. The first one is that we could only write a fixed value. And the second one is that we could only write 4 bytes at a time. And even though we could choose the location of that memory corruption to some degree, there are also some limitations and some of the fields in the guest context page that we just couldn't reach. However, this time around, when the certificates are refreshed, they are also encrypted. And so in practice, the data that is written is completely random. And also, the firmware writes a lot more data. So it writes roughly 3 pages worth of data to that non-volatile storage area to store those certificates. So once again, we don't want to attack the guest directly for all of the reasons that I went into earlier. And we want to attack a guest context page ideally. Last time, we attacked the UMC key seed. However, this time around, this won't really work. And the reason for that is that the UMC key seed is already random to begin with, and we can only override it with a new random value. And there's really no point in doing that, because like all of the guests will have random values. And last time, we could only exploit this if we could get 2 guests to share the same encryption key, which we can't do using this vulnerability. So we actually need to take a look at some of the other fields. And one of the fields that's really interesting is the so-called address space identifier. So after the UMC key seed has been programmed into the unified memory controllers, each of the VMs is associated with an encryption key using the so-called address space identifier. And what's interesting is that if we can corrupt the guest context page, and in particular, if we can corrupt the address space identifier, we can potentially trick the firmware and the memory controllers into using the encryption keys of another guest. And so the idea then is that we don't need two guests to have the same encryption key if we can just crop the guest context page from one guest to just point to that encryption key of that other guest over there. And so this way we don't need to have two guests share the same encryption key. Also, because we need to corrupt the whole guest context page, that's just how the vulnerability works, we also need to corrupt the policy field, and ideally we want to corrupt it in such a way that it has the debug flag enabled. Okay, so once again, there are problems. The first one is that there are only a very few number of valid address space identifiers. And the reason for that is that the UMC, the Unified Memory Controllers, of course, has to store all of those encryption keys, and it doesn't just have unlimited storage to store encryption keys. And so depending on the CPU model, there are roughly 500 or 1,000 valid encryption keys. And so this is also the number of address space identifiers that is valid. The address space identifier is a 32-bit values, so the chances of getting a valid address space identifier are actually fairly low. Another big problem is that, well, once again, guest context pages are encrypted, and so the address space identifier field and the policy field are also encrypted, and so this makes it so that the hypervisor can't just look at them and figure out what they actually contain. However, for this, there's actually a very nice solution, which is that AMD SEV-SNP conveniently has a command to just decrypt both of those fields in addition to a few other ones. And the reason this is allowed to work is that none of those fields are really sensitive, and if the hypervisor wants to know about those fields, the firmware will happily tell the hypervisor about them. Okay, so what we can do then is that we can repeatedly ask the firmware to refresh the certificates, and every time it does that, it will corrupt the guest context page using new random values. And we do this until we hit a very specific set of conditions. The first one is that, once again, the address space identifier needs to be valid, and the policy field needs to have the debug flag enabled. There are actually also a couple other conditions, but they're not as interesting, so I won't go into them. But in the end, the chances of getting all of the conditions right are roughly 1 in 20 million. Furthermore, we can corrupt around 300 guest context pages per second if we just hammer the firmware all the time. This might seem kind of slow, and this has a reason. Refreshing the certificates is a fairly slow operation, and so this is also why we can only corrupt such a low number of guest context pages per second. But in the end, if you do the math on all of that, and if you just continuously hammer the firmware all the time, and we expect to get the right conditions about every once a day. I mean, in the end, it's completely random, so you might get lucky, you might get not lucky, but that's what we would expect. What's really nice, though, is that we can actually do this before we launch the victim guest. So we just need a guest context page to point to some other guest. We don't need that guest to be already running. And so we don't need our victim guest to stay around for a whole day while we hammer the firmware. And we can actually do this well in advance. And once we've done that, we can actually use the same corrupted guest context page for multiple guests if they happen to use the same address space identifier as the one that's in the guest context page here. And so in the end, once again, I've written a proof of concept for this. For this particular run, it took like 1 day and 19 hours, and it took like 1.4 million. I needed to crop the guest context pages 1.4 million times, but in the end, we actually got a very small address space identifier, so it didn't need to be that small. In this case, it happened to be 31. And once again, I've used this vulnerability to then decrypt a secrets page. So once again, if you look at the first byte, you can see that it's 3, and you can also see some of the structures are very similar. And yeah. OK, and so this leads me to my last point, which is that I believe that those exploit strategies that I showed you here today are actually fairly reusable. If there are, my conjecture is that if there are other memory corruption vulnerabilities that allow a hypervisor to corrupt memory that's covered by the RMP, they will be able to use either of those strategies to actually turn this into something that can be used to leak secrets from the TE. The reason for why I believe that is that, first off, we can corrupt fixed writes, but we can also exploit random writes. It doesn't really matter. Also, the exploits are completely workload independent, so it doesn't matter if it's running Windows or Linux or a database or whatever. It works for all of them. And another point is that I actually discovered a third bug that I didn't have time to go into today. It turns out that this bug can be exploited using the very same strategy as exploit number 1. There are a few changes that need to be done, but the very basic idea of forcing two guests to have the same UMC key seed and then in the end have two of those guests to use the same encryption keys is completely identical, even to the last detail where we had to use the same location and all of that. Okay, so this leads me to my takeaways. The first one is that the hypervisor is very powerful, even though it's constrained by the hardware. And so the result of that is that because the hypervisor has a lot of control over the setup for different vulnerabilities, even very simple bugs can have a large security impact. So for example, the last bug I didn't have time to talk about today is actually null pointer dereference, and well, it turns out that we can actually turn this into something very useful, even though null pointer references typically aren't exploitable. The next takeaway is that I believe that firmware that's used by SEV, but also other TEs, really deserves a lot more attention. So when it comes to TEs, there's been a lot of research on CPUs and microarchitecture, and that is definitely very important research. But if we want to evaluate the entire security of TEs, we also need to look at the code that's actually running to support the hardware in doing all the stuff that it's supposed to do. And so this brings me to my last takeaway, which is that in order to assess the security of all of those systems, you should really demand as much transparency as possible of all parts of the stack. So obviously, that includes the hardware. Your CPU vendor probably won't give you the schematics for the CPU, but if they can give you the firmware, that's really great. But this also applies to the software that's actually running inside of the guests. So there are some people and some clouds that don't want to give you access to all of the code, but ideally, if you want to use a TE and you want to trust that TE, you should demand as much transparency as possible. Okay, so with that, thank you very much. All of the proof of concepts are available on GitHub. The repositories are actually still on private, but I'll set them to public within the next hour. And with that, thank you very much for coming to my talk, and enjoy Black Hat.